Okay, we shall get started. Thank you all very much for coming today. I'm very pleased to introduce our speaker, Dr. Smith, who comes to us from Stanford. We're also very pleased to have her here today because she agreed to fill in for us at the very last minute after a cancellation of a previous speaker. So it's wonderful to have someone who can give a talk for us like this, someone close by who I think has done some really interesting work to tell us about today. She comes to us by way of Texas, the University of Texas, with a PhD from the University of Maryland, and has a recent appointment as an Einstein Fellow at Stanford. And that's a 3-year position during which she'll be getting some work after you complete your PhD work. Postdoc is usually the next logical step. So it's wonderful to have a speaker who can join us from local close by on short notice. We're very grateful, and we really look forward to hearing about your work. Thank you so much for coming. Let's have a warm welcome to Dr. Smith.
Thank you very much. Yeah, I'm very pleased to come and talk to you guys today. A lot of what I'm doing requires some evangelism to kind of sell it to the astronomy community, so I really like to accept talks. I really like to kind of share this idea. The title of the talk is The Great Potential of Exoplanet Satellites for High Energy Astrophysics, and that kind of encapsulates the thrust of my research, which is sort of using high energy instruments and instruments in space telescopes, and even some ground-based instruments for purposes other than they were originally built. And this is going to be a particular example of that, and I'll focus on the main part of my research, which involves supermassive black holes and doing that kind of science with these satellites. But I want to get started by describing to you, or possibly reminding you, how we look for exoplanets in modern astronomy. So we are looking for the signal of an exoplanet passing in front of a star. And the way we do that right now is with space-based missions, so orbiting optical telescopes around the Earth that watch stars and wait for this signal to appear. And what's happening in that situation is that you have an exoplanet here, which is the black spot, and it's on its orbit around its host star. And then as it proceeds along that orbit, it comes along, and then the light from the star is eclipsed a little tiny bit by the planet. So its brightness over time goes down until the planet moves out of the way again, and then it flattens back out. So we can find a lot of planets this way, but it requires really, really high precision measurements of brightness, because you can imagine, that this is an exaggerated picture. Most of the time the planet would be a tiny speck like the size of that laser pointer versus the star, and so the amount of light that is blocked is very, very small. So this looks like an obvious signal, but it's actually very, very difficult to detect, and it's really zoomed in here to some extent. So what the kind of data that we get from these experiments are called light curves. And a light curve is a plot of brightness over time of any object. So here's just some examples of light curves. This is time on the bottom axis and the brightness of the source here. And here's a candidate exoplanet transit. Again, this is kind of noisier than the last one. And they're averaged here. So the actual data is the gray, and then they have to bin it in the black to actually see what's happening. Here's a star that's doesn't have a planet going around it, just a flat star that's not doing much. And here's another example light curve. So that's what I mean when I say light curves, is the object's brightness over time. The timing instruments on these telescopes are designed to take readings much faster together and without big gaps. So if you do this from the ground, you can only see them at night. So you have at least 12-hour gaps where you can't see it because the sun is up. And also the Earth is turning, so your telescope won't be able to see that part of the sky for more than a few months, and then you have to wait. So the light curves from the ground have a lot of gaps. They're not as precise. They're not from space. They have sky background to contend with. So we really have these state-of-the-art telescopes that are looking for these planets, and that was what they were built to do. And the main instrument right now that's the most famous and that's been the most successful is called Kepler. Kepler was launched in 2009. It stared at one part of the sky, one small patch, close to the Milky Way galaxy in the sky, because it's looking for planets in our galaxy, and it just stared there for 4 years. It didn't move, they couldn't point it, you couldn't steer it and point at anything else. It just looked at the stars in that patch and waited for any of them to have this signal. So think, it was looking for Earths, right? It was looking for planets like Earth, or maybe a little bit larger. And Earth is on a 1-year orbit. So if you want to see that orbit repeat twice to be sure it's there, you have to be watching for several years at a time if you want to be able to confirm that. And of course, you're going to find a lot more planets that have faster orbits and that are more massive, but you're going to find a handful of what we were looking for. And so, like I've said, the sampling is very fast. It's a reading every 30 minutes for 4 total years. of everything in this field of view with incredible photometric precision. And just to make the point of how successful this really was, I'm showing two plots here. The one on the left is before the Kepler mission, and the one on the right is after. The one on the left, the plots are planet mass versus orbital period, and the one on the right is radius. But the thing to notice is how many yellow dots there are. So Kepler found upwards of 3,500 candidate planets. And you can see that here's the mass of the Earth drawn on the plot, the radius of the Earth. A lot of these are Earth-like. Most of them are Neptune-like. But anyway, this instrument did its job phenomenally well. And it had a slightly tragic end, which I'll get to later, and that caused us to have to kind of do some fancy footwork. But this instrument was massively successful at this. However, all of the things that make this kind of satellite good for hunting exoplanets also means it's a really good instrument to do a lot of other cool stuff. So you can imagine that kind of readings, 30-minute measurements for that long staring at one part of the sky. You can get light curves of things that are not planets. You can get light curves of lots of things. Here are some examples of that. We can see how matter behaves around black holes. So normally black holes, you can't detect them if they're just sitting there doing nothing. But if they're accreting matter, so matter comes in towards the black hole and forms a disk as it starts to funnel down, and that's what we call an accretion disk, that glows very brightly in optical light, which is what we're looking at. So we can watch that. We can see a light curve of an accretion disk around a black hole. We can also see flares happen in white dwarfs. Pulsations of young stars, that's often called astroseismology. So we know that stars have these modes within them that cause them to kind of pulsate and vibrate. And until recently, we could really only do that well with the sun to this level of precision. But now we can really do astroseismology for lots and lots of stars on the HR diagram and really fill it in. And many, many more things as well. You might have heard of this weird light curve of a Kepler star that people thought might have a Dyson sphere or superstructures around it because it has this, the light starts to dim, but then it gets kind of weird and it doesn't quite get back up, and it stays, and its behavior is strange, and people came up with all these possible explanations, and some people thought it was aliens. More people thought it was maybe a swarm of comets or something passing in front. So there's all kinds of really cool stuff you can do with these data. But one in particular is cooler than the others. And that's this top one, which is my favorite thing to do. Specifically, I use this to look at active galactic nuclei. And active galactic nuclei are the centers of galaxies where there's a supermassive black hole. And there's an accretion disk around these, that's why they're active, and I'll show you in a moment. But this is the connection that I'm making for most of this talk, is the behavior of accretion disks in active galactic nuclei. So, what is an active galaxy? This is a galaxy, and this is a barred spiral galaxy. This is the type of galaxy that the Milky Way probably is, but we can't see it for sure because we're down in the middle of it. And if you zoom into the very, very center of this galaxy, very, very far, into a region about the size of our solar system, right there in the middle, you will find a supermassive black hole in the center. A supermassive black hole has a mass millions to billions of times the mass of the sun. Now, there are lots of black holes in the Milky Way galaxy that are 3 to 10 times the mass of the sun, and now with the new LIGO results, maybe 40 to 50 times the mass of the sun. But there's lots of these, and those are the ones that are born that are the corpses of stars. So large stars die, become black holes. There's lots of those, but this is a different beast. It's much larger, millions to billions of times larger, and those live in the centers of galaxies. We have one too. The one at the center of the Milky Way is about 4 million solar masses. That's kind of puny as these go. But all galaxies, almost all galaxies, have a supermassive black hole in the center. Some of them are actively consuming matter, so there's the disk around them. Some of them are lurking quietly like ours. It's not consuming matter right now, not an accretion disk of matter anyway. And when they do consume this matter, the disk heats up and it gets viscous, and there's torques and friction, and it heats up very much, and it glows in the X-rays and in the optical, and generates a very large energy output, and that energy varies a lot, so we can use light curves to study it. Here's an artist's conception of what that looks like. Down in the center of that galaxy, there's a black hole where that white point is, and then you have this accretion disk of matter that's kind of swirling in here, and then sometimes you have these big jets that are ejected from either side. So that's kind of the anatomy of an active galaxy. And oh yeah, so here is the acronym, Active Galactic Nucleus, or AGN, which is what I'll be using for the rest of the talk. So just as a review, active galactic nuclei, there's a zoom-in picture of the center there with the black hole. Actively accreting supermassive black holes in galactic centers, about 10% of galaxies have one of these in them. And they're variable in every waveband. And what I mean is that the flux changes a lot. So if you watch it, it doesn't just stay at one level of brightness. It gets dimmer, it gets brighter, it gets dimmer, it gets brighter in radio waves, infrared, optical, and X-rays. And gamma rays, actually. Okay, so why do we want to study this with optical variability? So theoretical work on accretion disks is very lucrative. People are making a lot of progress. What I'm showing here is here's like a cut through of the accretion disk. So the black hole is here is the accretion disk, and this is a simulation, numerical simulation, a hydrodynamical simulation, sorry, of the kind of processes going on in the disk. And this is great. However, we can't really test these theories that well in the normal way because these are way too small for us to image with a telescope. We can't take a picture of an accretion disk because these are around the black holes in other galaxies and they're very, very small. So the size of our solar system, again, in another galaxy, very far away. So we can't take a picture of this. Variability, though, the light that comes from it and how that changes and goes up and down is a direct probe of the conditions in the disk. So we know that the light is coming from the disk, and we see the light changing in time. So it's really the only direct probe of the accretion disk itself. Now, I told you before that Kepler stared at this one patch in the sky, and here it is. This kind of weird polygon here. And this is the galactic plane in the sky, the Milky Way. So they wanted to point it close enough to the plane that they were getting stars in our galaxy, so that they're getting a bunch of our galaxy stars. This is our galaxy. And look for planets there, but far enough that it wasn't so crowded that they couldn't tell what light was coming from what star, because it doesn't have infinite resolution. Unfortunately for us, this field of view of the sky, remember you can't point this telescope. It's here or that's all you got. It's too close to the galaxy, this galaxy, for mini AGN to be known in this field. So there's lots of surveys of AGN and active galaxies, but they're all safely far away from our galaxy so that we know that we're looking for other galaxies. So that doesn't overlap with a bunch of catalogs of AGN. There's millions of known AGN, but in this field there were only 2 when Kepler was launched. So the first step in doing this kind of work is to find AGN in that field. We know they're there, they just aren't cataloged because all the catalogs are in different parts of the sky. So what do we do? There's a 3-step process that we undertook to do this. So there's a telescope called SWIFT. It's an X-ray telescope. It has many telescopes, but one of them is an X-ray telescope. It's in orbit, like all X-ray telescopes. And we did a survey of that polygon field of view with the SWIFT satellite to look for X-ray sources. Remember I was talking about how the accretion disk gets very hot and glows brightly in optical and X-rays? When you find an X-ray source, it's a good chance that it's an AGN or black hole, but it could also be some other X-ray source. Some young stars are bright in the X-ray. There's neutron star binaries in this galaxy that are bright in the X-ray. So once you have your catalog of X-ray sources, you have to go take optical spectra with ground-based telescopes and observatories of each of those X-ray sources to see if they're stars or galaxies or AGN or what have you. And then once we decide which ones are AGN, we ask Kepler to monitor those AGN. So this was the kind of method. Okay, so that led to this wonderful acronym KSWAGS, which stands for the Kepler-Swift Active Galaxies Survey. This is the polygon, if you recognize that shape, of the Kepler field of view. These are modules, that's how it's kind of broken up. And the survey was of these red ones, the X-ray survey. And over here, it's just a diagram of the pointings of the SWIFT telescope in those 4 fields. So that's where we pointed the telescope at each of those spots to look for X-ray sources. Once we had the X-ray sources, we have to go and see which of them are AGN. And this is us at Palomar, the team, the KSWAGS team. This is the Hale telescope at Lick Observatory, and this is the Discovery Channel telescope at Lowell Observatory. So that's where most of these data all of these data were taken. These folks in the back here These folks really like X-ray bright stars. So for them, this was a win-win for the group, because either they were stars or they were AGN, and everybody's getting something that they want out of the survey. So that's really good. Here's some example optical spectra. So a spectrum is just what happens, remember, when you pass the light of an object through a prism, and it spreads it out like a rainbow, and sometimes there's bright lines which are emission lines, and sometimes there's absorption lines. So this is brightness over wavelength. This spectrum is a chromospherically active G star. So this is a star we'll revisit shortly. There were a lot of these lurking in our X-ray sample. This is the kind we were looking for, with these bright emission lines that's indicative of an AGN. And then we got some white dwarfs, or regular stars with white dwarf companions that were kind of mucking up the sample, in my opinion, but one man's trash is another man's treasure, so very good. Yeah.
Was the X-ray survey commissioned just for this purpose, or was it a separate passive survey?
No, it was mine, yeah, that we designed it for this, yeah.
What was the exposure times like for?
200 or 2 kiloseconds per pointing, yeah. So it's not super deep, but it's about 10 times deeper than ROSAT, and that's all we had to go with at the start. So anyway, here's some example types of objects from our sample. This was the target here. And we found about 30 new AGN in the field of view of Kepler in those modules that we surveyed. But we also found 63 X-ray bright stars, which were really cool. They did their own kind of project. I was convinced that these were equally awesome as AGN, and we should pursue them. Here's some examples of the spectra of those. And the idea of what these might be, like why do we have a bunch of X-ray bright stars, because most of the time stars are not bright in X-rays at all, is that you have two binary stars, and then one kind of starts to evolve. It does what's called filling its Roche lobe, so it kind of grows out over here. It doesn't really matter. The point, I'm going to show a cool movie in a second that makes this fun. But what the essential point of this kind of scheme is that eventually the two stars, form a single star that has kind of two cores on the inside. So it's kind of elongated, and in this process, the envelope expands and it becomes a little orange colored. So, because NASA cannot pass up an opportunity for a press release, even if your result is esoteric, the press office is very good at what they do, and we found this on October 27th. So, NASA decided that it would do this kind of cringeworthy press release called the pumpkin stars. And I think they're really interesting, and I'm glad so many people thought this was cool. They're not pumpkin stars, they're just orange round stars, but that's fine. So here's just some fun headlines from around the web that came out of this project, just in time for Halloween. And so I'll show this movie now. And you'll see the sources from our survey pop up here. Those are the modules we surveyed, and then you'll see it populate that with some of our funnest objects. There they are. Those are the pumpkin stars. This is one example, K-SWAG 71. So it rotates 4 times faster than the sun. It is much larger and is 4,000 times brighter in the X-rays. So something is weird with it. And here's the description of the plot on the previous page. I mean, I wouldn't have thought of it. So kudos to the press office for this wonderful video and for the clever term. So there were 93 objects in the study. Again, about half of that number is not quite right anymore, but at the time, about half were active galaxies. Now it's about a third. And it mentions now that the survey is ongoing in the K2 mission, and I'll talk a little bit more about K2 in the future. Okay, so we'll let them put their logo up here because of the wonderful work they did. Credit where credit is due. There it is. Wonderful. Okay. But now that the beautifulness is over, and then that's not my exact field of study, but I like it because it has headlines, so there you go. Yes, so Kepler was actually, as I have pointed out, not meant to do this. And so that leads to a pretty major problem with the data. So the spacecraft was designed to look for exoplanet transits, and so it treats its data with that in mind. It wants to do everything to that light curve to make it easier to see the transits. And here's the transit diagram again. This is periodic variability, so it happens predictably over time with the very, it's exactly the same period, and it's in a point source, a star. However, AGN are completely different. They do not vary periodically, they vary erratically. Not randomly, but up and down, up and down. We call it stochastic variation. So it's not periodic, and it's usually in these big galaxies. So we're looking at a small point source in the middle of this big extended source. And that causes a lot of problems. So you couldn't just use the Kepler light curves as they came down from the sky. You have to do something creative to make the data useful for your application, which turns out to be generally true when you're using instruments to do things that they weren't designed to do. But you want to maximize the scientific yield of instruments and projects, and so you do it. I had to write a pipeline that dealt with a few of these problems specifically. I'll just give two examples here because most of them are really painful to talk about. Kepler, the way it gets its light curve is it puts a little map around it here, like here, it puts a little box. We call it aperture photometry. It puts an aperture, this green box, on top of the source it wants to measure. And it takes the light from everywhere inside that box and puts a data point. Then it does it again 30 minutes later, another data point. That's fine if your source is a star, which fits neatly inside of that box as a point source. But if you have a galaxy like this, and the point source is in the box, but the box is also kind of like in and out of the galaxy, the spacecraft kind of drifts a little bit because it's in space. And that's okay, because remember, the light curve is everything inside the box. So if this star goes up here, and then it goes down here, and then it goes, that's okay, it's still inside the box, because you're getting all the light from the box. But if this happens here, and the galaxy starts to drift down here, there's less light inside the box, so you get this fake trend downwards. And it looks like it's coming from like it's really the source doing that, but it's not. It's this artificial signal from the source moving around. So the first thing you have to do is build these kind of custom-shaped extraction masks. And the second thing you have to deal with is that the pipeline on Kepler takes this wonderful, or not on Kepler, but at NASA, before they made it public, takes the data, which is the blue, so this is a light curve, this is brightness over time, and the blue is the signal from the source, and it fits it with this red curve and wipes it out. Because it's trying to get rid of anything that's not that period so that you can see it better. But this is what we want. Like, we want to see the variability that isn't periodic. So you have to go back to a very early stage in the data and kind of stop it from doing this. So anyway, this is not the most fun part of the talk, but this is what I spent like 4 years of my thesis just beating myself to death over. So I like to tell people about it because it really was a labor of love. But at the end of that, you get something really worthwhile. So AGN light curves. So this is a 3.5-year baseline of the Kepler mission. Remember, there's a data point here every 30 minutes for 3.5 years with a precision of 0.1 to 1%. And it's just better than anything we've ever had from the ground, anything we've ever taken, any kind of light curve from the ground of AGN. It just doesn't hold a candle to this. And we'll just zoom in here to make the point. This is 4 days of those 3.5 years with error bars. So this is really unprecedented. And the types of science we can do with this are really kind of revolutionary. And I'll just show you again. Here's just a few. Here's 3 of those 30 AGN. Just to give you a sample of kind of what we're seeing, the types of different variability that we see. This is, again, brightness over time. These are 3 light curves, 3 different objects. Some of the objects, we have a kind of rapid stochastic variability over the full baseline. This is rest frame days, so 1,200 days. This object is high redshift, so it's far away. The rest frame is only 500 days. But you can see it's kind of just hanging out, and then something bizarre happens, and then it just keeps on hanging out. And then we have objects that kind of have both types of behavior. So you have the erratic variability and these kind of discrete events superimposed. And this is just 3 examples of the sample, and they're just a lot of different types of behavior, and we want to kind of study how do those things change based on parameters of the galaxy. Yeah.
You making an estimate of bolometric luminosity, or is this just at whatever the wavelengths Kepler is operating at?
Yeah, unfortunately, well, it's very close to the bolometric optical luminosity because Kepler is a white light bandpass. So it's huge. They were going for every type of star. So they went, the Kepler bandpass is like 400 to 900 nanometers. Like it's the optical bandpass, which is really good if you're trying to get, an estimate of the magnitude, but not so good if you care about what part of the disk is varying, because you want colors to do that, and there's no colors. Can't do anything about that, though.
So it's variation in optical brightness versus time on the accretion disk.
Yeah, right. Okay. So now that we have light curves of this quality with like almost no gaps going on, then we can just do very straightforward time series analysis and take Fourier transforms of these light curves. And when you take a Fourier transform of a light curve, the output is called the power spectrum. And the power spectrum is just a plot of how much power there is in variations at some time frequencies, so like maybe a few days versus years. It can be quiet at the year-long time scale, like this one, but vary a lot at the day to week time scale, or it can be quiet on the day to week time scale like this one and vary a lot on much longer time scales or lower frequencies, which is longer time scales. So we take the power spectra. Here's some example power spectra. These are the same three objects as from the previous page. What we plot here is power spectral density. That just means how much power is in variations at a given frequency. So this is time. It's frequency, but you can think of low frequencies over here. It means it doesn't happen very rapidly. So this is what we get a plot of. What we're looking for in these things, if it's getting difficult to follow, are two signatures. The slope of this region here, the high frequency slope, so these are the high frequencies, this is a negative axis. High frequency slope, which is this region here, and whether or not the entire power spectrum is well fit by one slope. And that is not the case in this object. We see what we call a break frequency. So the slope is looking good for a little while, and then at some frequency down here, it bends and turns over and is better fit by what we call a broken power law. So these are the objects from the previous page again, and we see kind of examples of both. And just to give you kind of a flavor of the results from this particular paper without getting too in the weeds, here is just a histogram of the slopes from our sample. So that's this quantity here. And there's some predictions from accretion models on what those slopes should be. And one of the favorites is called the damped random walk model, and it predicted a slope of 2. And actually most of our objects have much steeper slopes than that. So that means that this particular model of accretion disks is not very good when we have this kind of really nice monitoring. And it was good from the ground. So the ground-based light curves said that this was about right. But the space-based light curves are looking a little different. And so that's kind of a new result. And then the time scales. These are some more power spectra. These are the ones that are fit by the broken power law. They're not fit by a single power law. When that happens, the place where that occurs, where that dashed line was drawn before, the frequency, you can transform that into a time scale, and that tells you the disk has a characteristic time scale at that time. So these are just the 6 in our sample that did have these breaks. And the time scales here range from 12 days to 53 days. So there's something interesting happening in the disk at 12 to 53 days. That time scale is it's approximately equal to a lot of different physical timescales in the disk, but it's a decent match for the orbital timescale of matter around black holes of these particular masses. So that's encouraging. We also found that these timescales increased with mass. So that's encouraging too, because if they're related to the mass, then we should see some type of correlation. But anyway, that's just 2 of the things that came out of that particular survey, but this talk is about using these instruments in general. So I want to move on to talk about kind of the current and future state of these satellites and how we can use them in the future. So Kepler was repurposed as the K2 mission in 2013 after the failure of its third reaction wheel. And what that means is that in order to point at that one part of the sky, it had wheels to help it in all 3 dimensions keep it stabilized and point there. And there was a redundant wheel built in so that if one failed, it could take over. But unfortunately, the redundant one then also failed. So the spacecraft could not point anymore at that part of the sky. That ended it. So 4 years was the maximum. It was supposed to be 7. Now, because humanity is tenacious and NASA people or Ball Aerospace people, I should say, are really clever, they came up with a solution that I think is just mind-blowing and totally amazing, which is that they decided they still have 2 wheels, so they have 2 dimensions, and they figured out a way to use the light from the sun hitting the solar panels to steer as the 3rd dimension. So they have 2 wheels, and then the light from the sun is called radiation pressure, is hitting the spacecraft, photons from the sun, and is providing this 3rd dimension to help steer. I mean, that was crazy. I thought I was doomed. This is my thesis. I was in the 3rd year of grad school, and then these people came along. I mean, it's just amazing. So I'll talk some about K2 and show you what's going on with that. The Transiting Exoplanet Survey satellite, Tess, is launching on April 16th, very soon. People are going down to watch the launch. It's going to be great. This is going to be the successor to Kepler in the US. And then there's some future European missions like Cheops and Plato that are very good potentially for this in the future. Although I haven't dialogued much with Cheops, but with Plato I have. So, K2. This is the rebirth of the Kepler mission. And what you can see here is a map of the K2 fields of view over time. And you'll see that they move. So this is just RA and DEC. But this patch is the same shape as the Kepler field because it's the same spacecraft. But because it's using the sun to steer it, it has to point along the ecliptic. So it has to point along the zodiac. You'll see the zodiac constellations in the background there. You'll recognize the familiar ones. So it can only point at one of these fields for 70 days, and then it has to move on to the next one. And that's kind of the compromise that they have. So still 30-minute sampling, but the light curves are only 70 days long instead of many years long. And the precision is good. The photometric precision is similar to Kepler, so that's pretty impressive that they can continue to have that level of precision. But the shorter baselines means you can do less in terms of AGN science. But you can still do some good stuff. So anyway, that's what's happening with K2. K2 is currently in its 18th one of these, and it might have another one in it. They don't know exactly how much hydrazine is left, so they're just going to keep moving it and keep doing it and keep taking proposals until it just totally dies. And many more exoplanets have been found in these fields too, so that's still the primary driver. So that's what's going on with the Kepler spacecraft now. And then, like I said, next month a new spacecraft is being launched called Tess. Here is the picture of it's a diagram of a little dude. Tess is really the successor of Kepler. It's an unprecedented and underused tool for high-energy astrophysics. So this is what I told the Tess people. I was like, hey, this is going to be really good for everyone, and you should, because Kepler made this mistake. It didn't market itself outside of the exoplanet community at all until much, much later. And that really killed it because, like I said, we found 30 AGN in those fields. But there's many more AGN in the Kepler field that we didn't have time to find before it was too late to get monitoring of them. Tess is not going to make this mistake. Tess has astrophysics as one of its main drivers on the poster, thank goodness, in addition to exoplanet science. It has similar photometric precision to Kepler, although it has a slightly different band pass. And it has the same high cadence sampling, so it still has 30-minute sampling, just like Kepler had. And the baselines are long. Baseline is how long is the light curve, how long does it last. But the baseline length depends on the position on the sky. And I'll just show you a little bit more about the spacecraft to explain why that is. So here is a picture of the Tess spacecraft. I did not design the spacecraft. I did not work in the lab that designed the spacecraft or the detectors, so I don't know a lot of the technical specs. But as it pertains to this work, I can explain how it's going to do its job. And I want people to try and use it. So yes, I want you to understand the situation. The spacecraft has 4 cameras. There they are. And those 4 cameras are lined up, can't really tell from here, but in such a way that they are kind of, they're taking vertical fields with respect to each other. The spacecraft will sit there in the middle and will image this is one of those vertical patches right here. And it will do that for 29 days. And then it's going to move to the next one. and the next one, and the next one, the next one, the next one. And it will do that for a year, and then it flips down to the other hemisphere. So it's going to start in this, looks like it's the north, but it's going to start in the southern hemisphere for a year, and then it's going to go to the northern hemisphere. What that means, here's that same sphere but tilted towards you, is that the patches down here are getting 27 days of monitoring, and then when the patches start to overlap, you get longer and longer baselines, such that at the top of the sphere here, where it's always got one camera on that part, you're getting up almost a year of monitoring at the ecliptic poles. And this dashed line, so this dashed line tells you that James Webb will be able to see that region for 200 days out of the year once it's launched. And actually the red part of this is very much coincident with the James Webb Continuous Viewing Zone. So the James Webb is the successor to Hubble. It's going to be the next huge space telescope launched into orbit. And there's a lot of interest in using it to follow up some of these exoplanet candidates to try and see if we can understand their atmospheres, or if they have water in their atmospheres and things like that. But James Webb can also look at things that aren't exoplanets, and in fact we'll be looking at many things that aren't exoplanets. So the baseline can be short. These baselines at the top are a little too short to do what we're looking for with AGN. Remember I told you the characteristic timescales were 16 to 50-ish days? You're not going to see that very well in 27 or even 54-day light curves, because you need it to happen many times before you confirm it. However, this is a good part of the sky. This is also a nice advantage over Kepler for extragalactic science, because instead of pointing at one field, you have the entire sky here almost, except for this gray zone. But you really do have a huge portion of the sky to look for AGN. And this does overlap with a bunch of surveys where we know there's thousands and thousands of AGN, so we can jump straight to the timing and skip all the X-ray optical spectra stuff, which is nice. We go just right down to business. Okay, so wrapping up here about astrophysical applications, obviously one of them is active galaxies, which I think is the best and most fun of the applications. You can also do cataclysmic variables. That's been a big interest. That involves a white dwarf. And the flaring physics there. X-ray binaries, so this is either a black hole or a neutron star with a companion regular star, main sequence star. And you've seen the pictures of this. There's the star, and then it has this kind of swirling stream of material that's accreting onto the neutron star or black hole, and that emits X-rays, because again, it's an accreting black hole, it's just a little one. But the physics might be very similar, and that's in fact one of the directions that you can take this, is to compare accretion onto these little stellar mass black holes, the little ones that are about 3 to 10 times the mass of the sun, with the big guys, with the million mass black hole ones. And there is tentative evidence that that process is not so different, even though the general relativity and space-time curvature in the presence of the big ones is much, much more dramatic. So that tells us a lot about accretion, and which is, it's super important. And I want to point out too that accretion doesn't just happen onto black holes. Solar systems that are forming, young stars, accrete matter in disks like this. So accretion disks are kind of ubiquitous in many different astronomical situations, and we don't understand them that well. You can also do astroseismology. So that's what I was talking about before, where you kind of watch the pulsations of these stars. And I really like the term galactic archaeology, which is what people are doing with astroseismology. So what these people are doing is that they're taking light curves of like all the stars in the plane of the Milky Way galaxy, like in the spiral arms, and then ones that are a little bit above that, what we call the thick disk, and then ones that are out in the halo of the Milky Way galaxy. And they can, from the pulsations of these different types of stars, they can get the ages of the different types of stars. And then they try to figure out what part of our galaxy formed first and like how that structure changed over time. So they're calling that galactic archaeology, which I think is, I just think that's so cool. And then Tess will be able to do that very well, because you will have this full sky coverage, whereas with K2 you only had kind of snapshots. And of course, anything else that you might want to look at that you think might vary, might have optical variability. So the future is super awesome and super bright. These missions are going to completely change time domain astrophysics. Time domain is really kind of the direction astrophysics is heading in. For a very long time, we thought of astronomy as looking at static pictures of the sky, a beautiful galaxy, a beautiful radio image, and we would do a bunch of physics on this. But in the past 15 to 20 years, we have really started to, as a community, view the sky as a very dynamic, changing beast, and how much insight that can give us into these processes is just really astonishing. And so with that, I'll thank you for your attention and take your questions.
Well, thank you very much. My first question for you is about X-ray follow-up to Tess regions. How is that going to be practical given the size of the Tess areas?
Yeah, so what we would really want to do with X-rays is to have X-ray light curves in addition to optical light curves. So we're going to get optical light curves, and it would be really good to have X-ray light curves at the same time, because the X-rays are coming from the center part, very close to the black hole. We don't fully understand why, like what the X-rays there are coming from. But it's related to the disk in some way. So if we see the X-ray variations being echoed by the disk, it will tell us something about the geometry of the X-ray source and the disk source. Now, like you say, we can't do that for everything because the sky coverage is enormous. And fortunately, we don't need to do specialized surveys because it overlaps with Sloan and a whole bunch of other wonderful things. And of course, the all-sky surveys like ROSAT and XMM SLU and stuff like that, we can follow those up with other things to see if there's AGN there. So,
gotcha. So more dependent on optical spectra
yeah.
than X-ray for hunting down
counterparts? Yeah, right. Well, so there's two things you can do. You can do Sloan for the optical spectra, or you can do X-ray sources from ROSAT and XMM, and you can't go get optical spectra of 300 or 400 random galaxies across the sky, but you can use infrared photometry. So you can use WISE colors and stuff like that, and then there's like some algorithms with the WISE colors that tell you that it's an AGN.
So you're just looking for the power law slope.
Exactly,
yeah,
right.
Gotcha.
So you cross-match, you take all the X-ray sources from ROSAT, you put them in through WISE, and then you do the algorithm with the colors, and then you get a decent cut. So there's a few tricks for finding AGN in Tess. A few tricks.
Questions for our speaker? Scott?
Yeah, your survey seemed to get right in at the beginning of Kepler. I mean, you were talking about the number of years of data you had, right? Mm-hmm. So we heard in talks over previous years about how that was set up to find quiescent normal stars. Could you talk about that process of saying we need to do this and getting in there early to say that you could have a set of targets? Yeah,
indeed. I mean, the fact that I was working at Goddard is almost the only reason that this was even possible on these timescales, because the Swift people were there with me and the Kepler people were at Ames, and we were working kind of together on this. And if I hadn't had direct connection to NASA itself, I wouldn't have been able to do it, because Kepler did not have a GEO office at all for the first couple of years. So the one that has 4 years or 3.5 years of monitoring, that's Zwicky 229, that was already known in the Kepler field and people were already looking at it. Then the others that have long monitoring, we quickly would, like the Swift data would come into Goddard, and then I would immediately reduce them, and we would ask for monitoring of the X-ray sources before we had the spectra. And that's the kind of the only way that we could. They didn't like that, but if we had the WISE photometry, we could make a decent guess and then ask them to monitor them. So that we had 5 that we were able to do that for. And then unfortunately, once we had all the follow-up and we had the full 30, well, there's actually 40, but we threw 10 out for different reasons. We got those in to be monitored, and they got monitored for 1 quarter. So they got 3 months, and then the reaction wheel failed. So we were working fast anyway, because we knew it would have 7-year lifetime, but it got cut even shorter than that. So it was very much, the timing was very delicate, because you had to get the X-ray sources down and reduced very quickly, and so that was kind of a challenge. And then the paper on the X-ray survey with the coordinates of the sources was out way after we actually started monitoring those sources. So people had to work with the archive. We intended it to be useful for people in the future to use Kepler, but by then it was just an archival, unfortunately. Very political.
Given the variability frequency we're looking at in the follow-up fields, we only had these 70 days of monitoring. But still statistically, I see with that number of sources, find some that have variation on timescales that you can measure. Just about what's the space density compared to the Kepler field versus the follow-up fields?
Well, you sample more of the sky, so that's good. You know, and some of these fields did overlap with Sloan and stuff like that, so we could get a lot of AGN in those fields. But yeah, you're talking about the lower masses. That's basically what we've kind of, the smaller black holes are very faster. So you're hoping that you get a bunch of the little ones that are varying quickly. At least that's the kind of the idea. But you know, that you suffer there because if what your goal is to see how mass correlates with all these different variability properties, how the disk is changing, and you can only look at objects up to 10 to the 7, it's not wide enough parameter space to do this very well. There's things you can do, like the total amplitude of the variability. That's kind of, you know, you can do that versus mass if you have these short baselines. You can look for interesting flares, you can look for events. But the broken power laws is too difficult. But you know, that's the idea, is moving forward, like how short is too short and for what masses. So like, you know, can you get down to 51 days with Tess and still do something interesting with 10 to the 6 solar mass black holes or not? And that's kind of an important, so what I've been working on is like taking a power spectrum from Kepler or light curve, doing the power spectral analysis and then shortening it. And then shortening it, and then shortening it, and seeing when I lose the information, when does the power spectrum become unuseful. So that's a real rule of thumb for LSST and for stuff coming up, I hope.
Reaction wheels have been a problem forever. Why don't they figure out how to make them last? Or why don't they put twice as many on the spacecraft as backups?
Yes, I asked
It really screws everything up, and I don't understand why.
I totally agree. I assume it has something to do with weight, but I would think might as well spend the extra fuel if it's going to keep the spacecraft in the sky. Yeah, no, I don't know. I mean,
How much do they weigh?
I don't know. I don't know. They're large. I've seen them. You know, but on a spacecraft that's about my size, you know, I guess that's something. But yeah, I'm not sure if the way they have to contact the mechanism doesn't fit more than 4, but I would love them to have 6 or 7. I mean, these are supposed to be like, and they fixed the problem with this crazy solution, but like, yeah, I ask myself all those questions too. I don't know.
I'm assuming there's some horrible Hobson's choice here, competing between design elements and things like that. I'm sure it's a compromise. Yeah, there must be a balance in there.
Yeah.
A room, I don't know.
When they stop working, it kind of kills everything else.
Exactly. Yes?
What's the predicted lifetime for Tess?
So the nominal mission, which it will always be longer than this, but is 2 years, 1 year on the lower hemisphere and 1 on the upper. It will definitely go for further than this. So every couple of years, there's a senior review at NASA where you have to pitch your instrument and say, you should keep funding my telescope and here's why. Tess will be very inexpensive compared to many of the other missions that NASA is doing because it's automated in this way. And most NASA missions get extended past their nominal lifetime because it's much cheaper to keep something in the sky and use it than to design a new mission and launch it. It's much safer that way too. So Tess, right now they have plans to go up to 8 years, and they have different schemes. So like they won't just do the hemisphere and then the hemisphere, they're gonna do other you know, looking at one place for longer and stuff like that. They got plans for all the years coming up, and they're actually soliciting from the community if you have ideas for, you know, a field you might want to look at or for some kind of scheme for Tess sampling, you can tell them that.
Do we know how many gyro stabilization wheels Tess has?
It has 4.
There we go. It's more than 3, so we've done well so far.
Yeah, but it has more fuel and is meant to be steered. So hopefully maybe put a little bit more effort into that.
You had one slide up in which you had light curves. I think it was 3 different objects that had characteristic curves. And I was thinking, I'm assuming Kepler has produced thousands of these light curves from all the objects that are under observation. Has anybody then just done a statistical analysis of the light curve without any preconceived idea of what object might generate it, but they're all similar? There must be a class of objects that are producing very similar light curves, but we may not know why even. But.
So this has been done for variable stars. But like trying to find variable stars in all of the Kepler light curves. So Kepler only monitored sources you asked for, so you don't have a light curve for everything in the field of view, but they did monitor a ton of stars to look for planets. So they just put in a guess sample of 100,000 stars, for example. And so those were getting the 30-minute sampling. Not everything in the field of view got 30-minute sampling. But people have written algorithms to kind of go through all the Kepler light curves to find Gamma Doradus stars or Delta Scuti variables or things that they can fit, you know, certain types of bumpy profiles to. AGN, yeah, you could do this. You could write a stochastic search pipeline, but I think the odds of them accidentally monitoring an AGN is really low because they were looking for point sources with stellar colors. So I think it could be, maybe there's a handful of AGN with 30-minute sampling out there that we don't know about. But we asked for all the ones that they ended up seeing.
I was just wondering if maybe there's an object that gets discovered somehow. I mean, there must be something going on similar with all these things to generate the same light curve.
Yeah, that's...
We didn't anticipate this, theoretically.
Yeah, that's a good point. I mean, people have gone through and looked for huge flares, like trying to find supernovae, basically, or trying to find, catch, a cataclysmic flare when it's starting off, or a nova. So people have gone through and just looked for massive deltas. And then there's some weird things that come out of that. I mean, that Dyson sphere star, so we still don't know what that is. And then there's a weird flare in a galaxy that it's like an extra long supernova or something. So there are some things doing that, but I think there's room for more big data kind of to take this on.
Right.
So that would be really great.
Any further questions? Yes, sir.
That's kind of it could be a potentially trivial question, but you mentioned that there was a different bandpass on the Tess compared to Kepler.
Mm-hmm.
Do you know what that might be and what the implications would be for the data from the light curves you're getting? Is that better, worse, doesn't really matter?
Such a good question. Yes, I have thought about this a lot. I do know the figures. So the Kepler bandpass is like 400 to 900, so it's white light. The Tess bandpass shifts to about 600 to 1100, so it's redder. And the reason that it's redder is because Tess is looking for exoplanets around M dwarfs, cool little red stars. Because the idea is if a planet is in the habitable zone of an M star, it's much closer to it because it's a colder star. So it will have a much faster orbital period, which we can actually see in 27 days. It might be as middle of 5 to 10 day orbital period and still be habitable if it's around a cool enough star. So they made the bandpass redder. Okay, that's good. For AGN, it's a little trickier because AGN don't vary that much in the infrared. They do a little bit, but a lot of the emission in the infrared from AGN is thought to be from dust, like glowing dust, and that wouldn't vary. It would just glow because it's not part of the disk. It's not coming from the disk. It's just coming from the stable population. So it's a little bit trickier. However, one possible good thing about this is that if we're looking far at higher redshifts, then we would be taking the optical part of the spectrum that varies from the disk and redshifting it into this bandpass, so we might actually be able to see accretion disks at higher redshifts than we would have earlier. So that's interesting. There's the give and take with the AGN on the Kepler Tess bandpass. So that's a very good question, yes.
So we're looking for smaller planets around small stars.
Yeah,
close in.
they're looking for habitable planets, period, and they can do that faster if they look for them around M dwarfs. But there's some new concerns about flares on M dwarfs, and if that would, so it's in the habitable zone, great, but if you flood it with gamma radiation once a year, it's not great prospects.
So maybe the right size, the right temperature, but ludicrously
Right.
deadly.
Yes, it's possible. It's possible that that's a relatively large problem.
Yeah, I was just thinking of LIGO, that you mentioned before, with the merging black holes. Would that also entail merging accretion disks that might have a spike that you would?
I love these questions because these are all the things I want to talk about. Yes, they would. If they're both active. So the one that it saw is probably just two black holes chilling out. But if you have two active supermassive black holes, so LIGO is looking for the little ones, the 50 to solar mass maximum. That's the signal it can see. The pulsar timing arrays and maybe LISA one day, the space-based interferometers, will be looking for gravitational waves from supermassive black hole binaries, which was my very first paper. And if they have accretion disks, both of them have accretion disks, you can see signals of that in the spectra. So my first project was looking for double peaked emission lines in spectra to try and find these binary supermassive black holes. In terms of the variability, you would see people think a periodicity. So you would have, for two reasons. One, they're orbiting each other. So from a line of sight point of view, you might see some periodicity of one disk and then the other. But also because if one passes in front of the other that close and they're that massive, it will lens the one that's behind it gravitationally and magnify it, the light you're getting from it, and then the orbital period proceeds. So people are looking for periodicities of 2 to 10 years to try and find these very close supermassive black holes that might be just about to merge. And hopefully, they're measuring that against the non-detections from pulsar timing arrays to kind of constrain the number of these binaries that are out there. And that's important for galaxy evolution models, because if every galaxy has a supermassive black hole at the center, and we think that galaxies merge a lot, because we see them merging all the time, we think that's how structure was built, there should be a lot of these binary supermassive black holes. So yeah, there's work definitely being done in that department, and it's very interesting.
Well, as we're approaching 5 o'clock, I think we shall wrap up at that point. Those of you with further questions to ask are welcome to do so afterwards. Our speaker will be joining us for dinner. If you'd like to come with, please come and speak to me at the end, and you'll be more welcome to join us. And with that said, let's thank our speaker again.